Welcome to our second workshop for Chemistry 1412, Colligative Properties. And on this workshop, we're going to actually focus on practical problem solving. A lot of the definitions that you're going to have, a lot of the definitions that you come across are going to be already covered in class, but the what you're going to see here is that doing the problems themselves can be a little bit tricky because there's a lot of different components to it. And there's effectively four different colligative properties that we're really going to be focusing on in this session and really in your class. And that is, we're going to be focusing on boiling point elevation, freezing point depression, vapor pressure, and specifically it's a vapor pressure lowering, and lastly, osmotic pressure. So these four colligative properties are going to be the ones that we are going to focus on the most. Now here's the thing. Colligative properties, colligative refers to a collection. And so it's the collection of particles that has the effect, but not the identity of the particles themselves. So it doesn't matter how many or what different types of particles you have, the colligative properties are going to be affected in the exact same way, regardless of what's being added to a solution. These are properties that are affected only by the number of particles in solution, not what the solutions are, or not what the particles are. So let's take, for example, this particular problem, number one. It says, what is the boiling point of an aqueous solution of 6.00 molar HNO3? That's 6 molar nitric acid. And it gives the Kb for water is 0.51, and the density of the acid solution is 1.125 grams per milliliter. Now, for any boiling point solution type problem, this is where we're going to want to keep in mind the formula for boiling point elevation. And the formula for boiling point elevation is, and that's a little bit thick, but I'll go ahead. Delta T for boiling point is equal to positive KBM. Now, alternatively, you may see this written as delta TB is equal to I KBM. I guess sometimes it's capital KBM. Now here's the thing. If I have if I have it written like this, that means that this is referring this M is referring to the molality of particles. The molality of particles. This is the molality of particles. Okay. So what that means, and essentially molality, keep in mind, is going to be the moles of the particles divided by the kilograms of the solvent. We have to emphasize that this is kilograms of solvent, not solution. So, moles of the solute over kilograms of solvent. That's the molality of the particles, and this is moles of particles. In this case, particles. However, if we use the I KBM, I is what's referred to as the Van Hoff constant. And the Van Hoff constant is effectively the number of particles, the average number of particles that each molecule of the substance or each group of the substance breaks up into. So for HNO3, if this was a perfect separation we would assume that there is 6 moles of H plus ions and 6 moles of NO3 minus ions, because when HNO3 breaks up, it does so into, and this is a strong acid, so it should completely separate, or close to completely separate. It would separate into H plus and NO3 minus. Now, technically speaking, this isn't 100% accurate because, in truth, HNO3 actually reacts with water to form H3O+, but for our purposes, this is sufficient. So, but what we'll find is that especially for higher concentrations, sometimes they don't completely break up as we'd expect. And instead of getting two particles for every HNO3, we only maybe get an average of 1.5 particles for every HNO3. And that would be the Van Hoff factor. So usually we use an idealized Van Hoff factor based on the number of particles it breaks up into. But if they give you a Van Hoff factor, you can use it here. If you have the equation that uses the Van Hoff factor, the I, then the molality here is no longer the molality of particles. This is just actually the molality of the solution, or the molality of the solute. So this in this case would be the molality of the solute. Because multiplying the molality of the solute times the Van Hoff factor gives you the molality of particles. Does that make sense? Okay, cool. And I certainly don't mind if you have your microphones on. Okay.
Just making sure.
Yeah, no, it's not a problem at all. Sorry. Um, I apologize if I gave that impression. Okay, so what is the boiling point of an aqueous solution of 6 molar HNO3? Well, let's go ahead and use this equation here. We're given the Kb. So I'm going to change my color here. We're given the Kb. So our Kb for water is this 0.51 degrees Celsius per mole. And the density doesn't seem to be part of this equation, but maybe it will be helpful. So one of the key things that you're going to have to do for these colligative property problems is you're going to have to actually calculate various different concentrations. And you're going to have to be pretty good with these concentration calculations. The first thing that we have to do is we actually have to calculate the molality. We're looking for the new boiling point, which means we're solving for the delta T. But to solve for delta T, we need to know the molality and the Kb. The Kb is given, but the molality is not. All we're given in terms of concentration is 6 molar. Now, what is molarity? What is molarity? I see 6.00 molarity. What does that tell me?
That's a meaning of a 6.00 mol. You say molarity, correct?
Uh-huh.
Okay. It to me it means that you have 6.00 moles of nitric acid per liter of solution.
There you go. So this is 6.00 moles of HNO3 per liter of solution. Okay? So that's what this means. And it's important that we're going to go ahead and split this so we can solve for the molality. Now, molality is still going to be the moles of the particles. So that's fine. Or molality is still going to be the moles of HNO3 if it's the molarity of solute. But we need to get this liters into kilograms of solvent. But the problem is this liters is of solution. So we actually have to separate the solute from the solvent, because what we have to keep in mind is that a solution has 2 parts. The solution is equal to solute plus solvent. Solution is equal to solute plus solvent. So if that's the case, we have 1 liter of solution, but we want to actually get the mass of the solvent, the kilograms of solvent. So the first thing we're going to want to do is convert the volume of the solution to mass. And we can do that using the density here. And once again, density can be used as a conversion factor, right? So I'm actually going to start with 1 liter. Um, can I erase that? Yeah, I can erase that. Where's my eraser? There we go. There you go. Now I'm going to go back to my drawing. So 1 liter. And keep in mind, when you see these fractional units, although 6.00 is 3 significant figures, you might be like, well, that one's only 1 significant figure. That's not actually quite right. When you have a fractional unit or a reference unit like 6 moles per liter, moles per 1 liter, this one is actually referred to as a reference number. And it's a reference to the actual measured value of 6.00 moles. So this reference number 1 actually has unlimited significant figures. Just keep that in mind. All right, so I'm going to convert the liters to milliliters.
So the bottom line is that the 1 liter is not included when we're counting significant digits.
Yes, exactly. So I have 1 milliliter is equal to 0.001 liters. You could also write 1,000 milliliters is equal to 1 liter if you prefer. But then I'm going to use my density of the acid solution to convert milliliters to grams. So this is milliliters, and I'm going to convert it to grams. And it's going to be 1.125 grams per milliliter. So once again, the 1 milliliter is a reference number, and the sig figs are the 1.125, that's 4, so my answer is going to be 4. And this is going to give me 1,125 grams. Now you might be wondering, why didn't I just convert that to kilograms? And there is a reason. Because I'm crazy. No. The reason is because we do not yet have the kilograms of salt. We don't have this is grams of solution, not solvent. It's the solution. Okay? I need to get the solvent. So to do that, I actually need to calculate how many grams of solute that I have, because there's no way to measure the grams of solvent directly. So I'm going to start, if I assume that I have 1 liter, which I kind of did over here, I assumed that I had 1 liter over here. If I assume 1 liter of the solution, that means I have to assume how many moles of the solute. How many moles of the solute?
Sorry about that. 6 moles.
Yeah, 6.00, right?
Mm-hmm.
And so this is the moles of HNO3. And I'm going to go ahead and convert this. I'm going to convert it to grams. Now go ahead and calculate the molar mass of HNO3 and tell me what you get.
How many significant digits do we normally use for molar mass?
I usually go with 2 decimal places.
So 4 significant, okay. Or 2 decimal places, okay, got it.
Same here. I use like 4 sig figs as well.
I mean, sometimes like if it's over 100, then I'll go with 5 sig figs, but I usually just do 2 decimal places because I feel like it reaches a degree of accuracy that is pretty good, but it's not necessarily going to be um, without having to do like a ridiculous amount of extra work, so to speak.
So for me, the molar mass that I got for nitric acid is 63.02 grams.
63.02, that sounds about right. So let's do 63.02. So 63.02. grams is equal to 1 mole. Mole cancels out, and I'll get my grams. 6 times 63 will give me 378. Now, I'm actually going to keep all my sig figs at this point because you're not kind of really supposed to round until the very end of any calculation. It's just good calculator, or that's good practice when it comes to doing calculations in science. You don't usually take sig figs until the very end. All right, so this is my grams of HNO3, which is my solute. So how many grams of solvent do I have? I have 1,125 grams of solute or solution, and solution is solute plus solvent. So how do I find the grams of solvent?
You would subtract the mass of the solute from the mass of solution.
Good job.
So I'm actually going to break my own rule. I'm just going to use the rounded value because I realize it's not going to make much of a difference in this case. So yeah, if I subtract 1125 minus 378,
747 gram.
747 grams, which I can convert real quick. Not that you need to show the conversion, you probably already know how to do this in your head at this point, but if you did need to show it, if you did want to show it, just to make sure, it would be 1 kilogram per 1,000 grams, and that's going to leave you with 0.747 kilograms of solvent. Good deal. Now that you have your solvent and you have your moles of solute, now here's the thing. A lot of things don't dissociate. There's a lot of things that we use that don't dissociate. So you just got to check at the beginning to see if this is a solution that would dissociate. HNO3, of course, does. Well, let's go ahead, and let's go ahead and just calculate the molality of the HNO3. The molality is going to be equal to the moles. And of course, we know we have 6 moles of HNO3. And that's going to be over 0.747 kilograms of solvent. I hope you're able to read my writing okay.
So far, so good for me.
I agree. So far, so good.
Okay. So then let's go ahead and calculate that. What do you get?
I got around 8.038 mole.
Yeah. So 8.03 molality.
I got 8.05, but I guess we're both within the error, so that's fine.
Well, you might have been using the unrounded value.
Okay, got it.
Okay. Which is for the reason why I probably should have used the unrounded value. But yeah. So but there you go. So that is the molality. Now, unfortunately, that's not where the problem stops. That's where it kind of just begins. Since we have the molality of the substance HNO3, we'll go ahead and use the Van Hoff factor version of this equation. The one up here, it says delta TB is equal to IKBM, and so if I use delta TB is equal to IKBM, if I assume perfect separation, what is the value of I?
2 ions. Or just
Yeah,
simply
I
2.
you can think of as the number of ions. So what is the value of I in this case? What did you say? You may have said it. I don't know if I caught it.
Oh, you're fine. I said 2 ions, or just two.
Yeah, 2.
Yes, yes, because nitric acid is a strong electrolyte, so it totally dissociates. You're right.
And then 0.51 degrees Celsius per mole. So 0.51 degrees Celsius per mole. That is our Kb that's given in the problem. And then we just plug in our molality, which is the 8.03. And then all we have to do is calculate that out, and what do we get?
I got 8.2 degrees Celsius.
That's right, because the 0.51 is only 2 significant figures, so 8.2 degrees Celsius. Now that is the change in the boiling point temperature. And so keep in mind that change in boiling point, it's going to be, we have to add the change to the boiling point. What's the normal boiling point of aqueous solution? Or aqueous means it's water, right? What's the normal boiling point of water?
100 degrees Celsius.
Yeah, so the new boiling point is going to be 100 plus 8.2. Now that 100, just for proper sake, I'm going to put it as 100.0. And that's going to give you 108.2 as your final answer. Does that make sense?
To me, yes.
How about you, Jeffrey? Awesome. So let's take a look at the next one. And I should make note. Yeah, let's take a look at the next one. So, a solution containing 125 grams of an unknown solute dissolved in 25 milliliters of cyclohexane freezes at negative 11.4 degrees Celsius. What is the molar mass of the solute? Now, the reason this is such a good problem is because this is almost exactly what you're going to be doing in an upcoming lab, and you're going to actually have to do these calculations if you have not already done so. So, if we look at, so a solution contains 1.25 grams of an unknown solute, and it's dissolved in 25 milliliters of cyclohexane, which freezes at negative 11.4. What is the molar mass? Well, the first thing we want to do is establish what is molar mass. Okay? What is the molar mass?
And, molar mass is basically the mass given for a certain molecule or certain element in grams per mole.
Yeah, and that's the key thing. It looks like I accidentally deleted everything because I chose the wrong erase tool. I apologize. Fortunately, it's on the video. But molar mass, and sometimes molar mass is represented, and not often, but sometimes molar mass is represented by this weird cursive capital M. But molar mass is essentially the grams of the substance that make up 1 mole of it. So if I want to calculate the molar mass of the unknown solute, I have to get the grams of the unknown, and I have to divide by the moles of the unknown. Now, what's given in the problem? Are either of those two given in the problem?
We are given the grams of the solute.
Yeah, the grams of the unknown are given. But what about the moles of the unknown? Is that given or no?
We're going to have to use the colligative to
Excellent.
derive that value.
Yeah,
Good job.
exactly. Yeah, exactly. So we're going to have to actually solve it with colligative properties. So here's what we're going to do then. Um, I don't have any information that would allow me to solve for moles directly, but I see a Kf here, which is a freezing point depression constant, and I see freezing temperature, which makes me think that I'm probably going to have to use the freezing point depression equation. Delta Tf is equal to negative Kfm. Now, if you're very perceptive, you might notice that I put a negative sign here, whereas you may not have seen a negative sign in your book.
Yeah, and I'm not sure if I agree with that designation, but because the relationship is a proportionality relationship. So the change in temperature is proportional to the to molality, and we replace the proportionality by a constant. I mean, you
But
know, uh-huh.
uh, what you'll actually find is that in different textbooks, they deal with this in different ways. In the Brown, LeMay, Bernstein textbook, The Chemistry of the Central Science, they actually do delta TF is equal to negative KFM. In the Tro textbook, which is probably the one you're using,
Mhm,
they use delta TF is equal to positive KFM.
uh-huh.
The reason that I think that the negative KFM designation is more appropriate is because boiling point, the colligative property for boiling point is elevation. So boiling point is increased, it's raised, but freezing point is decreased, it's lowered. So mathematically speaking, the change in freezing point is a negative change. It is a final, which is the of the solution, minus initial, or in this case, the solvent. So before you make the solution, the freezing point would be the 20.4 degrees, or rather, the freezing point would be 6.6. But after you make the solution, after you add the solute, the freezing point drops. It's a freezing point depression. And therefore, I think it makes more sense to have it as a negative KFM. However, if you prefer to use positive KFM, that's totally okay as well. You just have to keep in mind that when you get to the end here, you're going to have to subtract this from the freezing point, or if you do it with the delta TF is equal to negative KFM, it's a little bit more obvious that that negative is going to be applied to the freezing point and it's going to lower it. Does that make sense? I happen to like the negative KFM and Dr. Neely likes the positive KFM. Please feel free to use whichever works best for you, whichever makes the most sense for you, because ultimately that's what's important. Because like I said, it's not that there's one hard and fast way of doing this, and textbooks even differ on this. So, okay, so proceeding from here, we want to use the information that we're given. Effectively, what we realize is that we have the grams, but we don't have the moles. We need to find the moles if we're going to solve this problem, the moles of the unknown. The only part of this equation here that relates to the moles of the unknown is the molality. So it looks like we're going to probably have to solve for the molality here. So delta TF is the change in the freezing point. So the freezing point of the solvent is, and so in the final, so like I said, how I work this out is effectively delta T of the freezing point. You could say, or delta T of the boiling point as well. The in this case, the freezing point of the solution minus the freezing point of the solvent. Okay, so if that's the case, the delta TF here would be, what's the freezing point of the solution? What do you think?
Um, to me, it's negative 11.4 degrees Celsius.
Very good. Negative 11.4 degrees Celsius. What is the freezing point of the solvent?
That'll be 6.6 degrees Celsius.
Delta TF, then if you take this, negative 11.4 degrees Celsius minus 6.6 degrees Celsius is going to give you negative,
Negative 18.
yeah, negative 18.0 degrees Celsius with appropriate sig figs. Remember, we're adding and subtracting. It goes by the number of decimal places or the place value of the largest uncertainty, however you want to look at it. And the tenth place, so my answer stops in the tenth place. Negative 18.0 degrees Celsius. So then I can take my negative 18.0 degrees Celsius and pop it back into here. And then, and what Dr. Neely said before was correct in that if you do have the positive KFM version of this equation, you wouldn't worry about the negative sign. You just take the absolute value of the difference between the two. All right, so the KF value is 20.4 degrees Celsius per mole. And then, of course, we're solving for the molality. Okay, so then all we have to do is what?
And calculate the values to get the molality of the solution.
Uh-huh. And we do that by dividing both sides by?
Dividing both sides by the by the KF constant.
By the negative 20.4. Absolutely, very good. So negative 18.0 divided by negative 20.4. Negatives cancel out, and I get 0.882. Of course, I'll keep a couple extra sig figs because I don't want to round until the very end. 0.88235. And it's actually interesting when you're calculating numbers to exactitude in mathematics. One of the things that you'll find out if you run through the research is that there is a significant difference between using 4 decimal places and 5 decimal places. But between 5 decimal places and 6 decimal places, or 5 and 7, or 5 and 8, there's really not a significant difference in accuracy. So in mathematics, when they're going for the exact answers, as exact of an answer as possible, they typically round things to 5 decimal places, because after that point, the effort is not worth the outcome.
Oh, wow.
Just a little
I didn't know
interesting tidbit. Yeah, interesting tidbit there. So here we go, 88235. So 5 significant figure. It's actually only 3, but I'm going to put 5. And this is molality. All right, so now we have the molality. What now?
So for me, we're going to have to take the volume of the solution, which is 25.00 milliliters. We're going to have to convert it to into grams and then kilograms, and then it's not just a solution; it's the solvent. We're going to have to take that and multiply it by the molality that we had just calculated to get the moles of X, or the unknown solute.
Very good, Joe.
Very good. Yeah, absolutely.
Thank
So
you.
we first and you can use density as a conversion factor. Any fractional unit like density, you can use as a conversion factor. So Cyclohexane has a density of this. That means I can convert the grams to milliliters using density as a conversion factor. I don't actually have to write out the density is equal to mass divided by volume equation. I can just write it like this. 0.7785 grams over 1 milliliter. And now that I have grams, I can convert that to kilograms, right?
Yes.
So I want the solvent. This is the solvent, and I need kilograms of solvent to calculate the moles of solvent. So 1 kilogram is equal to 1,000 grams. And from there, I can use the molality as a conversion factor. Because molality means, just as molarity means moles per liter, molality, I could write this as 0.88235 moles per 1 kilogram. Does that make sense?
Yes.
Now you could use the equation molality is equal to moles over kilograms, but as you can see, using it as a conversion factor does actually save you a few steps. It kind of streamlines it, makes it a little bit more user-friendly, I think. But feel free to do it whatever way makes the most sense to you.
Actually, I like it. I like this way you're doing it because did it. I did it with the two steps. Using the definition. But
Mhm.
this is much more fluvial. I like it. Good job.
Thank you. So now we go ahead and we multiply everything on top, and we divide by everything on bottom, and calculate the moles. And what do you get for that?
For me, for moles, I got about 1.7 times 10 to the power negative 2 moles for X.
1.7 times 10 to the power of negative 2. Now, you should, in this case, get 4 significant figures. Well, actually, you should get 3 significant figures if we take into account the fact that the 0.882 is actually a 3 significant figure number.
Let's see. Sorry, I'm just like going through my calculations again.
Oh yeah, no problem, no problem. Now, you did an excellent job though. That is definitely the correct answer. And watching our significant figures, we start with 4, and the 0.7785 is also 4. The 1,001, those are definitional values, so they have unlimited sig figs. And then our last calculated value is the 0.88235, but technically speaking, it would only be 3 sig figs because the negative 18.0 is 3 and the 20.4 is 3. So our answer here is going to have 3 significant figures. And so this is point, and you can point, you did it in scientific notation, which is totally fine. I have to confess that I don't like to use scientific notation unless I absolutely have to. So I'm going to write it as 0.01717.
Oh, I didn't know.
Yeah. So here it's 3 sig figs, so sig figs only go out to the 1, but I'll keep the 5 decimal places. And this is the moles of the unknown. Of course, that's not the final answer, right? What do we have to do yet?
Oh, the final step is that we will divide the given mass of the unknown solute in grams with the calculated moles for the unknown solute to get the molar mass.
Absolutely. So the 1.25 grams is going to get divided by the 0.01717. But once again, this is technically only 3 sig figs. But the 1.25 grams is also 3 sig figs. So, and that's going to give us our grams per mole. And what does that give you?
Let's see, for me, I got I got about 72.8.
There you go. Excellent. 72.8 grams per mole. So if you can do that and understand it pretty well, you are locked and ready. Locked and ready to go for that lab on freezing point depression, which is coming up. Admittedly, that's quite a hefty problem. That is not an easy problem. There's a lot of steps there. You end up having to work backwards a little bit.
I
Any
like how we
questions on
have
that?
to. Oh,
Yeah,
sorry.
this is a hard problem. So Victoria and Jeffrey, if you did it also while you were chatting, yeah, really good job being able to solve this. It's a complex problem. There's a lot going on.
So Victoria, you were going to say something. I'm sorry. Go ahead.
Oh no, you're fine. It's just it's kind of humorous or in which like we have to like do like so many steps just to get the moles of the unknown solute.
Yes. Yeah. It's true. Like doing all that work. And one honestly, just one of the things that I notice a lot from students. Sometimes they'll do like, especially like the more intelligent ones. They'll do a lot of work, and they'll get the right answer for not the final answer, but they'll just be like, oh, I did so much work. Okay, that's it. I got it. But they'll
Oh
forget that
no.
what you're looking at is like, they'll stop at the moles of the unknown and be like, yeah, you did a great job. You're supposed to solve for molar mass. And you're like, what?
Indeed.
Yeah. No, it is funny. So very cool. Well, very cool. Any questions on that? We ready to keep going? All right. Um, Dr. Neely, you want to take the lead on this one?
Sure. You know, let's see how I can write. Maybe it's a little bit easier than the other one. So here
I
we
can be your
have.
stenographer if necessary. I can be your pen if you wish.
Okay, the pen. Okay. So here we have a problem where we have to find the vapor pressure of an electrolyte, and they tell us the molality of this electrolyte. And qualitatively speaking, what would you expect before we start attacking it numerically if the vapor pressure of water at standard condition is 22, let's see, if it's 23.77 millimeters mercury, what would you expect to be the final vapor pressure when we have an electrolyte swimming in water? So in other words, can you just tell me if the vapor pressure is going to go up or is it going to go down?
Um, the vapor pressure to an extent should be able to go down, especially since like you have more particles interacting on the solvent, which is the water.
Excellent. It's going to go down because there's now a solute that's reducing the number of. Oops, sorry about that. Sorry about that. Okay, so let's go and CA dogs. They're rescue dogs, by the way. Let's
Oh,
go
that's
and
cute.
thank you. So let's go and write the relationship first. Okay, so hold on. T Here's the T. Okay. Okay, so what I want to, is it, it's not writing. Hold on. I'll get it. Just 1 second. It's not writing. Hold on. Victoria or Michael, can you please write on the first line for me P of solution until I figure out how to get this going. P, okay, P, thank you. P sub solution, thank you, is equal to X solvent times P solvent. Thanks. Okay, great. So
you need to remove the text.
no, it's okay. Yeah, it's okay. But Michael's, yours is nice, but I guess Michael's is more. Professor DePaul is more conspicuous. He has figured out these platforms very well.
I like being conspicuous.
So the big concept when solving these vapor pressure problems, we just have to keep in mind the big concept is the mole fraction. So in order to tackle the mole fraction, can you write on the next line moles KCl is equal to, let's see, moles right. Yeah, I'm gonna have to play with this program offline to figure out why it's not writing, but basically,
I can be your stenographer. Just let me know what you want me to type.
oh, thank you so much. Oh my gosh, well, you're my stenographer. That is, it's a pleasure to have you as my stenographer. Okay, so moles of KCl is equal to moles of KCl is equal to, and I'm
KCl?
just gonna, yes, please. Thank you. Oh, actually, is it NaCl?
Yep.
I'm sorry.
No, that's good.
Okay, moles of NaCl. I need to.
Moles of NaCl is equal to?
It's equal to, the problem tells me that it's 2.5, so 2.50 NaCl. And then in the next line, we're going to do moles of H2O using using the dimensional analysis. So in the next line, if you could please write moles of H2O
Okay.
is equal to, we're just going to assume 1 kilogram because molality is per kilo or
Oh yeah.
yeah.
Yeah. So okay. So yeah, the 2.50 molality of NaCl. What we did was what Professor Neela was doing is she broke that down and said, okay, well that means we have 2.50 moles of NaCl per 1 kilogram of water. And
Right.
because we need to do mole fraction, that's why we're converting both the mole, well, we don't have to convert the moles of NaCl to anything because it already is moles, but we do have to get the moles of water. Water happens to be solvent, yeah.
Yes, yes. Thank you for the elaboration and the clarification. Indeed. So in the next line, let's go and figure out moles of water using dimensional analysis, if you would. So let's go and say moles of H2O is equal to 1 kilogram H2O. And then,
So you got to convert the kilograms to grams, right?
yes, let's go and. Now, if you're writing stuff, I'm not seeing anything.
Oh, you're not. You might not be on the
No.
right spot on the board. You might have to scroll down a little bit.
Oh, is everybody, Victoria and Jeffrey, can you see everything that Michael is writing?
Yes.
Oh, okay, interesting. Okay, well, as long as you guys are seeing it, I probably messed up the program. Okay, so, okay, so let's see. We
You
went
could
from,
also, you could also I'm projecting it to Blackboard Collaborate. So you could also look on from there and just tell me what to do.
okay, okay. So while I'm figuring it out, if you could complete this dimensional analysis for me, that'd be
Sure.
wonderful.
So we're going
Thank
to,
you.
grams of water is going to cancel out. That's going to go on the bottom. And then the moles of water is going to go on top. So 1 mole is equal to 18.02 grams, right? And that's just from, and you all know how to calculate molar mass, I'm sure, but essentially it's the mass of 2 hydrogens, 1.01 roughly, and the mass of 1 oxygen, which is 16.00 roughly. That just gives me 2.02 and 16, which add up to 18.02. I know I probably didn't need to do that, but just in case there's anybody who watches the video later on, I'm just wondering, where did that 18.02 come from? That's the 18.02 grams per mole. Okay, so now all we have to do is multiply uh, the 1 kilogram times 1,000 times 1 divided by 1 divided by 18.02, and we'll get our answer. And because that 1 is a reference value, remember, this is a reference value, so this is going to be that 1 kilogram is a reference value. So that is unlimited sig figs, which means the significant figures here is only going to be limited by that, only going to be limited by the 18.02 grams of water, which is another reason why we want to which is another reason why we want to make sure that we have this accurate, as accurate a molar mass as possible. Usually, like I said, at least at 2 decimal places is what I like to go with. So 1 times 1,000 divided by 18.02. And so this is 55. Okay, so this is going to be 4 significant figures, so 55.49. And I'm actually just going to take it to 3 decimal places, or a little bit further, just to kind of avoid those rounding errors that come in. So 49, and what the heck, I'll just do 4939. There we go. So that would be your moles of water. So now that we have the moles of water, and we also have the moles of NaCl, what can we do with that in terms of this equation up here?
We can use the moles of sodium chloride in water to find the mole fraction of water itself.
Exactly, very good. And what would the how would I solve for the mole fraction of water in this case?
In this case, the formula would be the mole fraction of H2O equals the moles of H2O over the moles of H2O plus the moles of of, of the sodium chloride. However, one more detail that we need to like add on here is that like we are dealing we are dealing with an ionic sorry, we are dealing with an ionic solute here, so we're going to have to multiply the moles of sodium chloride with the Van 't Hoff factor or constant to get the number of ions in the solution.
I was wondering if you're going to catch that. Very good, very good. I am
Sorry.
thoroughly impressed. Well done.
Yes, indeed. Good job.
So we're going to have to multiply that by 2. Now, in truth, interestingly enough, the Van Hoff factor for like a 2.5 molar solution of NaCl is actually closer to about like a 1.6, 1.7. You'd be surprised
Oh.
it's that low. But for our purposes here, and for pretty much any, unless they tell you an actual Van Hoff factor, you're always going to assume a perfect separation of strong electrolytes, even though in actuality they don't completely separate. So um, we're going to say that this is 5.0 moles of particles.
I understand. It's just like for my prof, he wanted us like to like assume full disassociation just to like save time like for like the calculations.
Oh yeah, yeah. Shame on me. I feel it. I don't know why I feel it necessary to share unnecessary information. No, no. Just I find it interesting. Sometimes it
No,
adds
it's
to it a little bit more
interesting.
fun.
Yeah, it adds spice. So no, thank you for doing that. It's
There
it's
you
like
go.
it's like adding spices on food. You know, you don't have to have it. You know, you can still prepare your meal without spices, but it can be bland. But if you add spices, it's you know, it just makes it more interesting. The same thing here.
There you go. Absolutely. That's a good analogy. I like that. Well done. All right. So then we have that's our mole fraction of water. So all we need to do at this point, because we're given the vapor pressure of pure water, is multiply our mole fraction by our solvent. Let's calculate the mole fraction, and then we'll go ahead and pop it in to our equation. So what do you get for your mole fraction?
For me, I got 0.917.
Okay. Actually, I'm not going to bother repeating that. I don't know why I did that, but yeah, I got 0.917 as well. Very good. Oh, bye, bye, bye. Okay. So now we're going to go ahead and plug this into our final equation. Pressure of the solution is equal to 0.917, and I'll add a couple more sig figs. 3, 5, yeah. Even though I know I don't have that many sig figs, I know I only have 3. I'll just add them anyway. But technically speaking, this is only 3. Oh, actually, I lied. It's not 3. This is 4 sig figs because I had 4 there. And when I add these two numbers here, I still have 4 sig figs. So my mole fraction is 4 sig figs. What? Bet you weren't expecting that.
What a
My
twist.
mole. Indeed. The mole fraction is 4 sig figs, actually. And the vapor pressure up here, it gives us 23.77. So my answer is going to have 4 sig figs. It makes a difference. So it's my pure solvent, 23.77 millimeters of mercury. And so I multiply those two together, and I get 21.81.
That's what I get. Yay.
Does that make sense?
To me, yes.
Awesome. Ooh, I'm missing a. Well, I'm gonna switch back over to the Blackboard Collaborate screen because I just realized that I don't have a way to insert the other thing. I'm actually gonna go ahead and pull up um, the colligative properties. Let's pull up colligative properties. Got my practice problem. Yeah. You know what? Actually, I'm going to drop it into Blackboard Collaborate. I don't usually like to do this because it does some funky things when you upload to share the file, but I think that's going to be the most efficient thing we can do here. Um, so, here we go. Okay, do it. So basically, the next one that I want to cover, we've actually covered 3 out of the 4. We only have 10 minutes, so we probably weren't going to be able to cover everything else in entirety. But I do want to cover, we can at least catch the last one, problem number 5. So I'm sharing the PDF file in the screen. You can zoom in with the zoom controls in the upper right hand corner, upper left hand corner of the screen. And there's you can zoom in to your comfort level for problem number 5. So the cruise ship obtains all the clean water it needs for cooking, cleaning, and drinking from reverse osmosis system. Yep, there we go. An average shower requires 17.2 gallons of clean water. How much seawater would be needed for a reverse osmosis system to produce enough water for a shower if the RO system had a running pressure of 55 atm and a running temperature of 25 degrees Celsius? Seawater has approximately 1.25 molarity in dissolved particles. So the cool thing here is that the osmotic pressure equation, for some reason, is basically the same as the ideal gas law. And this is not necessarily to be expected. There's not a clear reason as to why this is, but the osmotic pressure equation is the same as the ideal gas law. If you look at it, because molarity is moles over liters, right? Moles over volume. So if we looked at it like this, PV is equal to nRT. If I divided both sides by volume, there you got your N over V, and pressure is equal to molarity times RT. Because keep in mind, there's no gases involved here. This is a solution. So it doesn't necessarily follow that you would automatically use the ideal gas law to relate pressure and molarity for osmotic pressure. But it turns out to be the case. This is really kind of interesting. That usually for osmotic pressure they use the pi symbol, this guy, but it's going to be, pi is equal to mRT. And of course there is also the I, the Van Hoff factor constant. But in this case, because we're given the molality of dissolved particles, we don't need to worry about the I. We can ignore that. And this is really interesting because I don't know if you've ever been on a cruise, but if you ever wondered where to get all that water from, it would be abhorrently expensive for them to pull all their clean water from the port. They'd have to pay for all that water coming in. So instead what they do is they just suck up water from the ocean, run it through the RO, and they use that for everything that they need. And while this does have the perhaps undesirable side effects of slightly concentrating the dissolved particles in the ocean, because the ocean is so incredibly huge, the amount of concentration is relatively minimal, such that it doesn't really affect the plant life. And dumping trash in the ocean, that's another matter. So this question is really interesting because even though it looks fairly simple, it has actually a lot of moving parts to it. Basically, I need 17.2 gallons of clean water. And effectively, the osmotic pressure has a running pressure of 50, but osmotic system has a reverse osmosis system has a running pressure of 55 atm. So what you need to do is you need to figure out the concentration to which this seawater can be concentrated by the RO system. And the way that you do that is by plugging in the 55 atm for your osmotic pressure. Sorry, it's 55.0.
Hello?
Hi.
Hello?
So what we're going to do is take our 55.0 ATM and have a molarity, which is going to be 17.2. Oh, molarity is, sorry. We actually are looking for the molarity. This is the weird part about this. And R is the ideal gas constant, interestingly enough. Per Kelvin mole. Okay. And the temperature, of course, is 298. So go ahead and calculate that molarity and tell me what you get.
For the molarity, I got 2.25 moles per liter. Sorry for the cruddy handwriting.
No, it's good.
All right, so this is 2.25 molarity. Very good. So if it's 2.25, so if it's 2.25 molarity, that means we can only concentrate this 1.25 molar seawater to 2.25 molar. So that means we're going to do a little bit of a dilution equation here. Okay? And this is not totally obvious that this is what you would do, but if all the RO system is doing is extracting pure water, but leaving all the stuff still in there, that means that the constant, this is kind of like a reversion of the dilution equation. Instead of adding water, you're taking water away. So M1V1 is equal to M2V2. M2V2. So basically what happens here, can you all still hear me?
Yes.
Can you all still hear me?
You're getting
Okay,
cut.
good. Okay, so basically what happens here is that my initial solution is my initial amount of seawater, okay? My initial amount of seawater, which is, which I'm actually just going to leave as V1, okay? And then my molarity, initial molarity of the seawater is the 1.25. Can't write with this. Okay, 1.25. There we go. But the concentrated molarity, I now know that the most I can concentrate it to is 2.25 molar. I also know that the volume is going to be, well, actually, I don't know what the volume is. I don't know what the concentrated volume is. All I know is that I'm taking out 17.2 gallons of clean water. So I know that I'm going to take whatever the original amount was, V1, minus 17.2 gallons. Pretty trippy, right? Probably not what you expected. But yeah. So we don't know the initial amount, and we don't know the final amount. All we know is that 17.2 gallons is taken away.
It's a linear equation with one unknown. So you just algebraically solve it and
So then, yeah, all you have to do then at this point is to go ahead and solve for V1. It's just a little bit of algebra, but that'll get you your final answer. Oh, by the way, just before you go, I just want to post the complete. I mean, this is also up on our website, but I'm going to share with you a link to the complete answer key for this. You can click on that, and it'll pull up the entire answer key for everything that we've worked on. Because I know we skipped problem number 4, and if you want to get the complete answer key for the last problem, um, it's completely worked out as well. And that should hopefully be helpful. Oh, and so thank you. Yeah, thank you so much for coming. We really appreciate it, and we'll hope to see you next week.